So hello everyone, and thank you for the invitation to talk about today's my topic here today, which is the collective movement of glioblastoma cells and potential roles of jamming transitions in cell organization. No, the other direction. Okay, yeah, thanks. So before I get into it further, I will just briefly introduce you to the tumor entity in question. And if we talk about glioblastoma, we're talking about a primary brain tumor. And with the diagnosis of it was a median survival of approximately 15 months after it. So, and in comparison to other tumor entities, glioblastoma rarely metastasize, so rarely leave the brain. But on the other hand, it infiltrates the whole brain tissue, making it more so than other tumor entities a disease of dysregulated migration. And this was the reason why we started to look at glioblastoma migration. And as our model system, we used a confluent monolayer as shown here, and two glioblastoma cell lines, the DL229 and U138 cells. And for our internal control, we used a healthy brain cell type called the astrocytes. And as you just can appreciate by these videos alone, comparing just by eye with the astrocytes, you see they show much, our tumor cells show much more reorganization and proliferation. And to analyze this, we use a tool or a technique called particle image velocimetry, which allows us to obtain local flow fields of our cells, and some examples are shown here. And when we started to analyze these flow fields, we just first naively looked at the speed as a function of time in our system. And in black, we see here the astrocytes as expected from these videos. They were by far the slowest compared to our two tumor cell lines here on top. Yet, just the speed alone is potentially quite a poor proxy for cell body translocation. So we looked at the passes traveled of the cells. Here are some examples showing for the astrocytes. You can see they barely moved and are very stationary if you compare this to the movement path of typical tumor cell fields. And to quantify this, we introduced a parameter we called preserved neighborhood, which is basically just the relative numbers of cells that did not make new contact to any new cell during our measurement time. So high values is indicating a stationary system or more stationary system, while low values indicate a high amount of reorganization. And just looking at these values again, we see what we expected from our videos. So our system in that sense makes sense. So we can recapitulate key factors of glioblastoma migration, showing high reorganization, high speeds compared to the healthy brain cells. And during our measurements, we noted that the tumor cells were far more elongated when we were looking at their shape compared to the astrocytes. And to quantify this, we used a shape factor defined as the ratio of the circumference of the cell over the square root of its area. And we noted in the case of astrocytes that their shape factor was below a critical threshold of 3.81, which was associated with the onset of jamming from some theoretical models, while for tumor cell lines, this value was way higher, associated with a more fluid-like phenotype. So, and with these observations, we looked into a literature because we were wondering if it would be possible to induce a jamming transition in our tumor cells. So transferring them from a state where they're fluid-like, allowed to freely move, into a state where they have like a polygonal shape almost, but more importantly in our case, are confined to their space. And according to literature, three key parameters are involved in such transitions. The first one being cell density, and increasing cell density was always associated with a slowdown of delay and eventual migratory arrest and this jamming transition. And then there are two more parameters, adhesion and fourth generation or tension. And these two parameters were, according to all models studied, always mutually counterbalancing each other. So if adhesion was associated with a slowdown, then tension was associated with an increase in migration, and vice versa, depending on the model. So with these key parameters that we wanted to look at, we started to tinker with the equilibrium of tension and adhesion by applying pharmacological drugs to our system. And results for our first tumor cell line, the LN229, are shown here on the first line. And in black, we see again the speed as a function of time for our untreated cells, and the reddish and bluish curves show the results after we applied different drugs to different applications. And I think it becomes quite clear that we first of all lowered the speeds. And not only that, we also show that the reorganization was reduced, having a more spatially static phenotype of our cells, with values reaching those of astrocytes that we considered it to be in a migratory arrest. And we also looked at the shape factor, and we're seeing that the shape of these cells got indeed more polygonal, reaching or getting even below the critical threshold associated with the onset of jamming. So we reasoned from those and other experiments and measurements we did that after we applied this particular set of drugs, we indeed could induce a jamming transition. Now, if you compare this with our other cell line here on the bottom, we also saw the decline in speed. We also saw reduction in reorganization, but looking at these numbers here, we can still conclude that they are in a highly fluid-like state and show great amounts of reorganization. And this is also more or less reflected by our shape factor that, albeit it declined, stays still way above the critical threshold. And thus we reason they are still in a fluid-like state. Okay, we have at least one cell line where we could induce jamming transition into. So we wondered what role tension and adhesion were actually playing in the system. So we set out to measure those properties using a bunch of methods called like traction force microscopy, atomic force microscopy, different labeling strategies, etc. And it turned out that in the cell type where we could induce the migratory rest into, the equilibrium of tension and adhesion was turned in favor of tension. While in the case of the cell line where we could not induce the migratory rest, the equilibrium roughly stays the same. So the ratios of those parameters were comparable before and after treatment. So we reasoned that in our system, tension was indeed associated with the slowdown and the eventual migratory rest. This was further supported by our measurements on these healthy astrocytes, which always had the highest tension and lowest adhesion in our system. So having at least a rough idea about the role of these two factors, we wondered next what role cell density in our system could actually play. Okay, now and therefore we just simply prolonged our experiments, because this allows cells to proliferate more and thus attaining higher cell densities. And we once again looked at the reorganization parameter we introduced, and we found for one of our cell lines to actually go into a state of migratory rest with very low reorganization. It's also shown here now in these videos where there's, well, still something going on, but it is way less reorganization than initially. But if we compare this to our more fluid-like cell line, we do not see any change as a function of cell density over time. So we wondered why this might be, and as you might have seen in this video on top already, we saw a transition of the organization in these cells from an initially rather unorganized state into a state where cells align with each other, pointing in the same direction. And to find out what kind of structures these cells in our system may form, we went back from a step back from our live cell imaging approach, going into looking at larger cell population. In this case, we have a cell population spanning 1 × 1 centimeter. And what's seen in this image is the heat map of the cosine distance of the cellular orientation. So similar colors implying similar orientation of the cells. And this, we can clearly see that there are large regions of cells that are oriented in the same direction. And we can also see that there are more or less steep gradients in the orientation. And when we look at these orientations further, we of course find regions that are roughly oriented in the same direction as shown here. It's also shown in the live cell videos. But we could find breakdowns in these organizations, which resemble topological defects as found in liquid crystals, for example. And the most prominent ones were the ones that had like half an integer defect topology, as for example this comet-like defect shown here, or this trefoil defect shown here. And in very rare occasions we even found whole integer defects as these aster forms here. So having observed these defects, we looked at the evolution of the nematic order parameter in our system as a function of time. So we went back to our live cell imaging approach. And just to make sure that this is not an artifact of the cell lines we used and we were employing, we added two more to the mix. One that's showing no signs of self-organization and the other that's showing signs of self-organization. So, and as we looked at the two cell lines here that show signs of this self-organization and alignment, as expected, we see a gradual increase in the nematic order parameter, while for the two cell lines where we do not saw initial signs of self-organization, we still had non-zero nematic order parameter, but it stays rather constant. As this parameter was calculated over our whole field of view, we wondered if there are, on smaller spatial scales, if there is order evolving, especially in our unordered cells. So we looked at different spatial scales and analyzed the nematic order parameter as a function of space and time again. This is shown in these heat maps. And I want you to look at this LN229 cell line, which shows, as we can see here on a large scale, only very little order. But if we look at smaller spatial scales, so in the order of 100, 150 microns, this means encompassing groups of around 50 cells, roughly. We see that there is a certain amount of nematic order emerging even in this particular cell line. So this might be indeed a universal effect in glioblastoma that they tend to order for high cell densities, but this remains to be evaluated. And nonetheless, we could also learn more from these kind of analysis because we did not know how the range of the order actually was. So we wondered if this would be a short-range order, a quasi-long-range order, or a long-range order. And as you just can see from this graph alone, as a function of space, obviously it's no pure long-range order because it is decaying as a function of space. But when we plotted the nematic order parameter as a function of coarse graining factor, we saw for our self-organizing cell lines that they were following a scaling law with a characteristic scaling coefficient that was approaching approximately minus 0.1 as a function of time. So we have increasing order and we have a quasi-long-range order. Otherwise, we wouldn't have this scaling behavior. Interestingly, even for our unorganized cell lines, or let's say better, less organized cell lines, we also saw that they followed a scaling law, albeit there was no temporal evolution in the nematic order. And as the last step, we of course wanted to know whether this ordering could in any way be associated with the escapes of our cells from a migratory rest if they show this kind of alignments. So we looked how well the orientation of the cells actually aligns with their movement direction. And this is, as an example, shown for one of the cell lines here in the self-organizing cells. And you can see already that even initially at the time point of 0, that more velocity vectors were oriented in the direction of the orientation of the cells as in the perpendicular direction. And every time, this orientation alignment only increases. Notably, this alignment is not of a unidirectional alignment, but rather a bidirectional one. So you have an alignment in the orientation and its opposite, implying that even in this state, there is no real polar order, but really whether really a nematic in this case. If you compare this with the same analysis for our rather unorganized cell lines, we can obviously see the difference in the orientation of velocity and orientation vectors, rather resembling a random orientation. And of course, we did this analysis in a bit more evaluated way. We looked at the amount of vectors that were oriented in roughly in parallel as a function of time and compared this to what's expected for a random distribution here in red. And we can clearly see for our self-organizing cell lines as a function of time and this also with cell density, the alignment between velocities, the movement direction of the cells and their orientation increases and is way higher than what's expected for a random distribution, while we do not see huge changes over time for our apparently less organized cell lines. And this we reason that these alignment may indeed be associated with the migratory escape from high cell densities in our system. And with that, I just want to briefly summarize the results of our work. I talked about the role of tension and adhesion in our system, and I hoped I could demonstrate that tension in our system might be most likely be associated with the slowdown of movement and the eventual induction of a jamming transition. We also looked at the role of cell density as a potential inducer of migratory rest, and here we can demonstrate that in a system-dependent way, the cell density can be associated with the slowdown of cells, but there appear to be ways to escape this migratory rest with the help of cellular alignment of velocity and orientation of the cells. So these cells can indeed show sort of spontaneously form self-organized structures with a quasi-long range borders. And of course, there are a lot of open questions to this. So what about the role and stability of just topological effects that we have shown you? This data is currently under evaluation, so I only have very little information about this yet, as well as the effect of this smaller ordered cluster that we found even in our unordered, apparently unordered cellular populations as well. So, and with that, thank you for listening and to all the people that were involved in the analysis here. Thank you.
Do you have any questions? The audience? Well, I'll start. Okay, you go ahead, please.
The difference in orientation of cell you showed before depend for sure of the interaction between the cells themselves.
Yeah.
Did you investigate this aspect?
So, we do have
because in animatic crystal, for instance, you have people interaction quite before.
So we're not in the classical system of pneumatic crystals. So there's the field of the active pneumatic, where they introduce like self-propulsive particles inside. And according to frameworks from there are two parameters that can be transferred to our system. And then we're basically going back to what we've seen for the jamming transition, that adhesion, if we increase adhesion, these models propose that we see an increase in the alignment. And if we increase tension or force generation, we see a decrease in the alignment. And so it's basically, it appears to be connected on this level. So that we're working in a very similar parameter set. But have we exactly evaluated the interaction in our system? Not precisely under disturbance, let me put it this way. We have ideas for the basal level. So of course, when I showed you the measurements for adhesion traction force microscopy, of course, we do have some measurements of it. And there it appears that the adhesion in our, we have it for one of those two cells, so take it with a grain of salt. There it appears really that the adhesion between cells is higher in the ordering cells, and tension somewhat similar. So force generation is somewhat similar. So it would be in this line of this proposed models, but this is, we are in the realms of speculating here. But this answers your question, that is.
How many cells are in? I guess you use a dish, Petri dish, putting your cells. How large is it, and how many million?
Yeah, in such a field of view, initially there are like, I mean, per experiment, we have, for each condition we have at least 60 to 80 fields of view. So that being said, upfront at least, and initially in our field of view there are around 300 to 400 cells. At the end of our measurement, it's 300 to 400 in such a field of view. Like, kind of depends on the cell line, because the cell sizes are different, and because we wanted to start with a pattern density of 1. So of course there's some variance. And the end of our experiments, it's way higher. It can be triple that amount, because cells proliferate quite a lot.
After
because we're measuring
3 days.
Yeah, after 3 days. Yeah.
Thank you.
Convergence of order is not, it can, under this results not be only dependent on cell density. So there have to be other, like, ongoing dynamic processes be involved. What they are, different story.
I have another question very fast because I see so many parameters. So which is the one, or they are all connected, or which would be the one that if you modify will change the most of the other parameters? I mean, if it's if I can answer it, or maybe there is no answer. But I was wondering because I make this questions because to me, as a biologist, I see the ability to give a number, a parameter to this behavior. If you can associate a specific parameter to a more aggressive behavior, maybe as a biologist, you can think of using that parameter to target the cell and stop it somehow. So we are looking for targets. So I was wondering, in all this, which is the one that maybe you would target the most? For example, is velocity, for example, something that will affect the organization, or being self-organized is better, meaning that more aggressive or less aggressive? Self-organization is more close to probably normal behavior.
Yeah. If I had to decide for one, which I clearly wouldn't want to do if not forced, I actually would go with the organization. Because there are other in vivo studies showing that at the invasive fronts of glioblastoma, that these organized structures occur, and that if they show those organized structures, they appear to be more infiltrated into the brain, which is the main reason for relapse after treatment. So if I would be forced to choose one, it's probably this. But on the other hand, you shouldn't neglect cell density as a factor at one, because what we see here are all emergent phenomena. Because for example, when we treated our cells with the drugs, we also looked at what does it do with the single cells. So when we got it in isolation, and here we had for all basically cases we had a slowdown of the cell of the movement, a slowdown of the dynamics, albeit not always very high. But on the single cell level, these cells even sped up, so showing the opposite effect.
Okay.
So we do need these crowding effects to actually emerge the structures and have get these properties that we actually see.
Okay, thank you. Okay, thank you so much.